Okay, so let's talk a little bit more about the definition of the surface energy, which we're referring to here as gamma. Okay. So in the previous set of notes, we had defined gamma as being the excess energy minus T times the excess entropy plus P times the excess volume minus sum over I of the excess number of species I times the chemical potential of I over the area. Okay. And so this is the area of the interface. And so another way to think about the surface energy is to say that, let's say we were to look at the surface energy of the diffuse interface. So let's say we were to plot as a function of position the enthalpy per unit mole. So this green line will be the molar enthalpy. So we would have a molar enthalpy in one phase, so we would have Hm of alpha, and then that would cross over to some other molar enthalpy, Hm of beta, Hm of beta, as we went from one phase to the other, right? And we could also plot on the same plot T, the temperature, times the molar entropy, right? So we know that since the two phases are in equilibrium, that the Gibbs free energy of the alpha phase has to equal the Gibbs free energy of the beta phase in the bulk. And so H alpha minus Ts alpha has to equal H beta per mole. Let's do this per mole. Minus T times S beta per mole, right? And so we know that the difference between right, we know the difference between the enthalpies has to equal T times the difference between the entropies. Delta Sm. Okay. So if we were to plot T times the entropy, right, over here it has to be equal. So this is T times Sm alpha. And over here it's T times Sm beta. But in the middle, it doesn't necessarily have to be equal. So we could have a crossover like this. And this region in the middle here represents a region where the two free energies are not equally balanced, and we could plot also as a function of x. We could plot gm, delta gm, which would be or gm, which would be hm minus tsm, right? And that would essentially look like this. It would be 0 in the pure phases, and then we'd have some bump here in the middle as we cross over between the two, and we could integrate over this volume, and this would be the surface energy is the excess free energy per area. So integrated over this distance as we move from one phase to the other. Okay, so that's one interpretation of the surface energy that's related to us crossing over from one phase to the other. Another way of thinking about the surface energy is to think about it as the work required to create a unit of interface dA. So we can think of it as a relationship between an amount of work done, and that's equal to a surface energy times an amount of area created dA. And in that context, we can write down an expression for the energy of the system, or a change in the energy of the system, differential of the energy, which would be related to TdS minus PdV plus sum over I mu I dNi, plus an extra contribution that's coming from the interfaces, gamma times dA. And then in this context, gamma by definition is the partial energy of U with respect to A when we hold the entropy, the volume, and the number of species fixed. So if we were to integrate this, that implies that we can write a non-differential relationship, just like U. Typically we would write U is equal to TS minus PV plus the sum of all the chemical potentials times the numbers. But now we can add a gamma A term, right, which implies that we can turn this around and write an expression for our gamma, which is U minus TS plus PV minus sum over mu I Ni over A. And what's interesting to point out is that these two pictures are not so different. This is the Gibbs free energy of the entire system. And here we are subtracting off this, which is the Gibbs free energy of the bulk phases. So this takes out the contribution, zeroes the contribution when we're in the bulk phases, and leaves just this excess contribution that exists around the boundary. Now, we still have this arbitrariness associated with where to put the Gibbs dividing surface, and so there is a convention as to where it's typically placed. So technically, and like we said, for these definitions, this is totally arbitrary, but it's typical to put the Gibbs dividing surface at a location such that the excess volume is 0, and for the first species, which is typically the solvent species, the excess number per unit area is 0. So this is for the solvent, the majority species. Okay, good.